All right, here. You guys got any questions? We'll start with some of those. Paul?
2.3, number 13.
Okie dokie. So this one just asks us to evaluate the limit. If it exists, anyways. God bless you.
Thank you.
So, oh, hi, Jillian.
Miss Payne emailed you. We had a lab today.
Oh.
So everyone was late to Xbox.
Okay,
Yep, sorry about that.
that's okay. No problem. What were you doing in your lab?
We did a hydrate analysis lab.
That you involve a titration?
It did not. No, just heating of the substance. No generation.
Okay. Oh, so like a calorimetry thing?
Yeah.
I gotcha. Trying to burn off all the water.
All the way, yes.
Yep. Okay. Cool. All right. So Paul, obviously, if we do a direct substitution, you get something over 0, right? Which is bad news bears. If we try to reduce this, the natural thing to do would be to factor the numerator. So that would be x minus 3, x minus 2 over x minus 5. And obviously there's no reducing that can happen there, right? So what do we say?
Oh, I just reduced one. Yeah, I thought I just was missing something.
No.
Spent a lot of time.
No, there's just nothing more to do. I assigned the odd one so you can check in the back of the book too. I think it says does not exist. I just looked. Yeah, that's okay. I just want to make sure what we're calling that, if that was going to be infinite or does not exist. You're welcome. Teagues.
29 and 2.3 piece.
Sure. Blake's like, that's a good one.
Great choice, Tegan.
Thanks, man.
Okay. So right away, again, if you try direct substitution, you notice you get like 1 over 0 minus 1 over 0, which is bad news bears. So I think probably the thing I would start with would be to just make a common denominator between the two fractions. And we might end up having to multiply a conjugate also, but we'll just see where that takes us. So I'd have 1 minus square root 1 plus t in the numerator over t times square root 1 plus t in the denominator. Everybody okay there? If I look at that, again, if I do a direct substitution, still have something over 0, right? So, well, in fact, it'd be 0 over 0, which is doubly bad. So I think probably what I would try here is to multiply by the conjugate with the numerator. Tegan.
Sorry, you just multiplied the negative 1 over t by root 1 plus t?
Yes. Yep. That's all I needed to make that common denominator. So probably I'll try this. I think that'll reduce down to a t in the numerator, and then I'm looking good. So the numerator becomes 1 minus 1 plus t. Is that okay there? So I'll have negative t on top, which is great because that's going to cancel with the t on the bottom. Oops. Mr. Kulik was very bad here. Almost forgot that.
So you would mark it off on a test. Like you mark the question wrong on a test.
I would not give you full marks if you dropped a limit.
Like one limit.
Mm-hmm. So at this point now I can do direct substitution, right? Now that I've canceled those t's. Everybody agree? So when I plug in 0 to t, I'm going to get 1 times 2. So it should just be negative 1/2. So that one was sneaky because you had to make a common denominator and then multiply by the conjugate. And it was even sneakier because the conjugate you need to pick was the numerators and not the denominators. Whoa, yeah. How would I know to do that? I don't know, just experience. I mean, I eyeballed the denominator and went, well, that's not going to help me any. You know, like, nothing's going to cancel out nicely for me in a way to where I can, like, reduce out the t. Because this is really my issue, is I just got to get rid of that thing. So, multiplying the top and bottom by root 1 plus t wasn't going to get me there. Wasn't getting me a t by itself in the numerator, so I scrapped that idea. I could do that by inspection and actually have to do it. I could just look at it. Blake?
So for 2.5, could you do number 49?
Sure. Oh, okay. $49. Says if f of x equals x squared plus 10 sine x, show that there is a number c such that, oh, well, you couldn't have done this yet because we haven't done the intermediate value theorem.
Cool, because the answer in the back of the book just made no sense.
Yeah, this is like a proof, but...
Cool, okay. Then I do have another question.
Sure.
So number 27.
In the same section?
Yep.
I think the last class asked about this one. Maybe not. Maybe they asked about it, the other 27 and 2.3. Oh, okay. It says, gives us this function. And asks us to use theorems 4, 5, 7, and 9 to explain why this function is continuous at every number in its domain and to state its domain. Well, hopefully the domain part should be pretty easy, right? The domain should be x's in negative infinity to 2, union 2 to positive infinity. Is that what you got? Everything except for 2?
I got 2.
Oh,
like,
I'm sorry.
root
Yeah,
2.
sorry. Cube root 2. Yeah. Thank you. Thank you. Yeah.
That's you're only dealing with stuff in the denominator.
Yep.
Right?
Jillian.
Can you explain the notation you just used right there?
So that's an interval notation. So that's saying all the numbers between negative infinity and positive root 2, and then between positive or positive root, or cube root 2 and positive infinity.
Okay.
So it's basically because these are parentheses, it doesn't include that ending value, so it's everything except for
Oh, that makes sense. Okay.
the root 2, or cube root 2.
And that's just simply because it's in the denominator, right?
So here's what I would say. So if I'm just going to kind of piece through this, that's what kind of function? Polynomial, right? Domain is all real numbers. This is what kind of a function? Cube root. The domain is all real numbers. So the cube root of a polynomial, still all real numbers. So the only thing I have to worry about then is the rational function, which is whose domain is restricted by setting the denominator equal to 0 and solving. Worth pointing out, how do you know there's just one zeroed for this? Or one real zero?
It's a cube root of 5.
Well, it should have 3 roots, right?
Oh.
So the way you'd want to think about this is as a difference of 2 cubes. Bless you. And if I set that equal to 0, the solutions there will be imaginary.
So, I don't want to be that guy, but how are we able to know that without having to write that all out? How do we know that those answers are imaginary?
Great. So this is the difference of 2 cubes factoring pattern that we would have learned in Algebra 2. The thing that's nice about the difference of 2 cubes factoring pattern is that the quadratic piece always has imaginary solutions to it. So as soon as I had to use that factoring pattern to solve this, in fact, just recognizing that I was going to use it was enough to tell me that all I got is 1. Only got 1 real one.
Because so no matter what, if you have a difference of cubes, no matter what, we're going to have
just one.
One night. Okay.
One real.
Cool.
And the same
Remember that.
And the same thing goes for if this is the sum of cubes. The only thing that changes are the signs, but all the results stay the same. So still just one solution for that. One real solution for that. Jack.
So were you able to use the cube root of 2 cubed because it's still equal to 2? So it's so equal to make the difference of cubes?
Yes. Yeah.
Okay.
Yeah. So that's how I rewrote 2 as a perfect
As a
cube.
perfect cube, so you can do the factoring pattern.
Yep, exactly right. Yep, precisely. Sneaky, huh, guys? Blake.
Sorry.
That's okay.
But so for 2.3, number 64.
Okay, I got some flipping to do here. Did I sign 64? I think I retracted it, but we can talk about it anyways.
If you didn't, we don't have to talk about it. It's perfectly fine.
Yeah, this was one where I think I went back and said, no, that's not the same. That's not what I thought I was assigning.
Let's not do it.
Yeah, I think I mean for 62 to be the last one
Okay, cool.
on the version or the edition 7.
Cool. Weird. Because isn't it like the one with the circles and then the lines? Yeah.
Yeah, it's just a little bit of a hassle. It's more than you need to do.
Okay.
You're not gaining a lot of extra insight. It's just a hard problem that's kind of fun, but it's just hard.
Okay.
So it's not like it's not something that's going to show you something neat. That's going to be helpful. It's just kind of just like this.
Is that like the kind of test that's gonna? Is that like the kind of question that's going to be on the test?
On your test
Yeah.
that I'm going to give you?
Yeah.
No, man.
What's the vibe? What's the vibe of the quiz?
Oh, you want to talk about the homework quiz already? Sure. So we're gonna do it on the computer. We're going to use the My AP questions. So I'm going to give you 10 of those multiple choice My AP questions. I'm going to score it banded the same way we did for the homework practice, where like 8 to 10 is a 10, 7 or 8 is a 9, etc. Okay with that? It'll cover up through like continuity, like that would be the last topic that would cover through. And I even told fifth hour was asking about partners. I told them it's like, if you want to work with a partner, that's fine, but the bands are going to get thinner. So like your 10 band is going to be 9 or 10 correct instead of 8, 9, or 10 correct. Like all the bands are just going to shift up a little bit because you have an extra person. I'm going to expect, more correct responses for your score, which again I think is, and you're fair. You can do either one, right?
Grade 5. I gotta sleeve of probably ones for you.
Oh shoot.
Look, guys, it won't be that. It's not that bad, right? Did you do fine on the other one?
Decent, I think.
Yeah,
Yeah, I did good on the other one.
it'll be fine. What's up?
Are the questions they're gonna be similar or like the same, like as the My AP we took before kind of thing?
They're going to cover more content, right? But the format is still multiple choice. It's still kind of the same style of questions. Like mostly they're things that you could use your calculator on, but it's not terribly helpful for you. Right? Like most of the time they gave you something that's like, yeah, I could use my calculator to do this, but like there's no sense in getting it out for the most of them because they give you the graph or they give you the whatever, and it just kind of conceptual-ish. It's okay? Feel fair-ish? I like having some wiggle room there, right? Like to know that you can get some wrong and still get full marks. It's a little bit of a relief, right? Much less stressful, I imagine. Which I think you guys probably have enough of. Right? Okay. We good? Feel okay about like what to expect homework quiz wise?
Yeah.
Okay.
So so 2.1 obviously, 2.2, 2.3, and then 2.5.
Yeah.
Okay.
And I don't even think I have any. I don't remember for sure, but I don't even think I have any intermediate value theorem stuff. I think it was just through the content we had covered last lecture. Let me just look real quick. That's fine. Let's look at that. So, That's just okay. Oh yeah, I even went back and organized this in a linear-ish fashion. Okay. That'd be okay. Yep. Yeah, this is, I would say up through what we did in the last lecture. Not even anything that we're going to still have to finish in 2.5 or that we're going to do today. Is that okay? Reasonable-ish? Give you some idea? Again, it's not one of those things that, because the format's like not really something you can super study for, right? It just kind of, I'd want to make sure I've reviewed my definitions on things, like what does continuity mean, and like what does, like how does the squeeze theorem work, and that kind of, what is a limit, definition of a limit, what can I say about that, or those sorts of things. But by and large, it's just, like making sure you understand kind of the concepts involved. Is that okay? I'd say short of making sure you've kind of played around with the homework a fair bit and reviewed a little bit of the definitions and, theorems and vocab and stuff, I wouldn't spend a lot more time. If you've done the work and you know the names of stuff and what it means, you should be good. It's not like it's, the right answer's on the page there somewhere. You just have to figure out which one it is. That's the only thing I really have budgeted for that time as far as I'm concerned. I think I have 10 questions for 40 minutes. If you're 4 or 5 minutes a question, that's probably not absurd for where you were at anyways. Obviously, once you get going, you're going to need to move faster than that, but we're not worried about speed right now. We're just kind of getting used to that format. Okay? It's okay. All right. You guys ready to pick up in 2.5 here? So we have one more topic to talk about in 2.5. And that's the intermediate value theorem. And this is one that I see on the AP exam a fair bit. When I went back and kind of looked through some of the old test forms and stuff, this is something that comes up a good amount. And I'm going to abbreviate that as just IVT for intermediate value theorem. And I think even the AP tends to do that. There's like a couple of these 3-letter abbreviated theorems. So anyways, let's say that we have some function f that's continuous on some closed interval. When I say closed, what do I mean? The brackets are at the end. And then let's also say we have some number n that's between f of a and f of b. And then we also have to assume that f of a doesn't equal f of b, because then there's nothing in between it, right? Okay, if you have that, then there exists a number c that's in the open interval from a to b, such that f of c is equal to n. Oh, that weird backwards e is just a abbreviation for there exists. I probably shouldn't have used that. I just do that stuff automatically sometimes. That's like a super common math abbreviation. So now you've seen it. If I use it again, you can feel free to be like, what's the backwards e again? You can ask as many times as you want. You don't have to use it yourself. You can just write the words there exists. But that's like a mega common math phrase, so mathematicians have come up with an abbreviation for it. I don't know why backwards e was the abbreviation. Don't ask me that. But it is. All right, so this is pretty wordy, right? What the heck does this mean? It's like kind of a Noidoi theorem once you've seen it. So let's say we have some continuous function here that goes from like over some interval from a to b. Everybody's okay with that? So that means that this y-coordinate down here would be f of a, and this y-coordinate here would be f of b. You guys agree with that? So if I pick any value in between f of a and f of b, I don't know, like say that's my n. What the intermediate value theorem says is that you can go and find some value c such that n is f of c. which of course it is, right? If I have a continuous function and we go from f of a up to f of b, somewhere in between there I have to pass every number in between there, right? And since it's continuous, I know I can take that y coordinate and find an x coordinate that matches up to it. That's all we're saying. It's like, oh, well, sure, of course. You know, if it was 10 degrees out this morning and in the afternoon it's 50 degrees, was there at some point during the day when it was 40 degrees? I mean, depends on your definition of like how temperature works. Real talk, AP Chem people, is temperature continuous? Is that a continuous function? It's not. Why not? Energy is quantized, like energy changes in discrete packages called quanta. This was Max Planck.
Does?
Yeah. Now, are we able to measure that minute of a temperature change? No, man. But like technically speaking, from a quantum standpoint, energy is discrete. Like it changes in whole number, like discrete amounts. But like, can we measure that outside of a laboratory setting? I don't think so. But
There's a certain temperature that you
yeah, but you're talking about like
Yeah.
hundreds of decimal places back is where you'd find that the jump where it's like, oh, there's nothing in between. But like, let's be real. Like in our real life, you never experience it. Like that's one of the weird things about that at the macro scale, everything feels continuous, right? That it's like, oh yeah, of course, energy is continuous. And at the quantum scale, the subatomic scale, it's like, oh, these things are not continuous. They're discrete. It's very strange. Anise, we're totally off track.
From your perspective,
Yeah.
why is calc required for business? Like, just not being like condescending. Or
No.
whatever, just like.
Can
that's off.
I table that until
Yeah,
we
you
get
can
a
table.
little bit further, because you'll come up and see the application
Yeah.
in another week or two. We'll start seeing that,
Alright.
and it'll come up and it'll be like, okay, sure.
Okay.
And it's not for business, it's for economics, is where the calc comes in. That's the place where it's like, yeah, we want to have some calculus here. Mostly just for a conceptual. You're not going to be doing problems, like calculus problems. You're going to use it conceptually. But that's the place of why they're looking for it. And we will talk about it in the course. So
Do we get to solve any like economics related things?
probably. I haven't gone through and read every single story problem that I have available to me, but for sure, if I see one, I will pick it out. But there's a bunch of terms that are in economics that basically equate to like things in calculus. Like I think like marginal gains and stuff. I'm not familiar enough with economics to really to remember them all, but I think that's one. Those marginal things. Is that an economics word? Yeah, I think that those things end up being calculus things. They're really just like Calc 1 things. They're not even like Calc 2 or 3 things, but they're all differential calculus rather than integral calculus. That means nothing to you right now, but it will by the end of this semester, or by the end of the year. Anyways, let's do a quick example on how we can use the intermediate value theorem. Most cases are going to be things that are kind of proofy. So questions will be like, show that, which is basically, we're saying prove. So show that this equation has a root between 1 and 2. So if you're asking to show that something is between two things, intermediate value theorem is a excellent tool for that. So the first thing I need to do is, if I look at the intermediate value theorem, the function I'm working with has to be continuous. So that's the first thing I need to do. So let's just call f of x equal to 4x cubed minus 6x squared plus 3x minus 2. What type of function is f of x? It's polynomial, and which we know is continuous everywhere, certainly on the interval 1, 2. We don't need continuity everywhere to be able to use our intermediate value theorem. We just need it continuous on the interval in question. Everybody's cool with that? Okay. So we have that. What I'll do then is I'm going to evaluate f of 1 and f of 2. F of 1 is going to be 4 minus 6 plus 3 minus 2, so that's negative 1. F of 2 is 32 minus 24 plus 6 minus 2, so that's 12. Okay? So the value of n that we're interested in between negative 1 and 12 is 0, because that's the equation we're trying to solve is equal to 0. So we notice that f of 1 is less than n, which is less than f of 2. So we can say by the intermediate value theorem, there exists, I'll write it out this time, a C between 1 and 2 such that f of C is equal to 0. So we're done. There's my root. It's called C. Did I find what the value was? No. Did it ask us for the value? No, just asked us to show existence, that there is one in there. Now, what did we really do here? I want to point out just graphically what this really did, because it's one of these no-doy things. So here's 1 and 2, right? So at 1, at one was, when x is equal to 1, y was equal to negative 1. And when x is equal to 2, y is equal to 12. And we're continuous. Did this pass the x-axis somewhere? Of course it did, right? That's all the intermediate values theorem is saying here. Since our function started at 1, negative 1, and ended at 2, 12, and it was continuous the whole way through, of course there has to be a place where the y-coordinate was 0. Of course there's a root in there. Right? Fairly simple idea, right? When you draw the picture, it's like, yeah, you know, of course. Of course it has to be the way it is. So you guys feel okay there? Luke?
Can you do an example where it doesn't exist? Well, it's not,
I mean, like if you wanted this to equal 1 point, or like 0.5
yeah, sure.
or 7,
Yeah.
those all still work because they're in between 1 and 12, or negative 1 and 12. Like it doesn't matter.
Okay.
Don't have to be 0.
Our n is whatever we're solving for, and then if it's in between. But then how? Is it just saying like if n is between there?
Then we have to have some x to go with it. Something must have existed to give you that output.
Okay.
There's some input that would have had to give you that output.
Okay.
Now, when would this fail? Well, the easiest place it's going to fail is if you don't have continuity. If your function isn't continuous, this will not work, because you could have had something like, you know, this, and obviously doesn't have to cross the x-axis if we don't have continuity. You could have some big jump discontinuity or whatever. And even if like the limit exists everywhere, that's not enough, because you could have a situation like that where you have a hole, a removable discontinuity right at where you need it. So you have to have continuity. That's the place where if this doesn't work, that's why. Does that feel okay? Okay. That was it for 12.5 or 2.5. Let's do 2.6 now, huh? So here we're going to be talking about limits at infinity, and asymptote, or horizontal asymptotes. So let's put on our time traveling suits and go back to our Algebra 2 class. Let's say we have a function that looks like this. Do you guys remember what we call these kind of functions that look like this? Rational function, very good. Now, do you remember how to find the asymptotes for a rational function? So the vertical asymptotes you're going to find by setting the denominator equal to 0. Now that has no solution in this case, right? No real solution anyways. So there are no vertical asymptotes. Are there other asymptotes here? There possibly are a horizontal asymptote or even an oblique, a slant asymptote, right? Do you remember what we needed to do to look at, or what we need to look at to find those? The degree of the numerator and the degree of the denominator. That's correct. In this case, they are equal. In the case where the degrees are equal, we had a horizontal asymptote. And that horizontal asymptote would be located at the leading coefficient of the numerator divided by the leading coefficient of the denominator. So we'd have the horizontal asymptote at y equals 1. Does that ring some bells? Yeah. And if I have a horizontal asymptote, what's really happening here? Well, the limit as x approaches infinity of f of x should be 1, right? As x gets very, very big, we're getting closer and closer to 1. Or the limit as x approaches negative infinity of f of x should also, or could also give me 1, right? One of those two things should be true. I think for this one, both of them are true. What's this going to look like? Yeah. Both those two things would be true. Now we've done something here that we haven't done ever before when we wrote those limits. We ever put an infinity down there? We haven't to this point. No, an infinite limit equaled positive or negative infinity. Here we have approaching positive or negative infinity. So these are limits at infinity as opposed to an infinite limit. But let's define what we mean by that, right? So let f be a function defined on some interval, and we'll say like a to positive infinity. Then the limit as x approaches positive infinity of f of x is equal to L means that the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently big. Right, so basically we're just saying we can get as close as we want to L by just picking progressively bigger and bigger values of x. Everybody's okay with that? Now this is for positive infinity. How does this definition change for negative infinity? Yeah. Yep. So rather than writing a second definition, I'm just going to do that. And just put a couple updates in for red.
Wait, is the arbitrary close to L be requiring x
to L. Yeah, by. That should be by.
Oh.
Sorry. Couldn't read my own penmanship. Paul.
You explain this again. It's not
So here's L, right? Here's f of x. And I can, that gap between L and f of x, I can get it as close, as small as I'd like, just by picking x's further down, right?
Got it.
So it's basically just saying the further I go, the closer to L I'm going to get. So this is going to give us to our calculus definition for horizontal asymptote. So again, very similar to the vertical asymptote definition, right? The vertical asymptote definition is either the right hand or left hand limit has to go to positive or negative infinity. Here, for horizontal asymptote, the left end of your graph or the right end of the graph has to be approaching that value L, right? As the x's get either sufficiently big or sufficiently small, they'd have to be going to L. Either is fine. Both is fine. Everybody's cool? All right. Let's look at an example. Let's say we want to find the horizontal asymptote for the function y equals tan of x, or tan inverse of x. What do you want to do first? If I'm looking for the asymptotes here, shoot, I'm looking at a picture, right? So there's y equals tan inverse of x. I'm going to actually just change the the y scale, so it's a little bit easier to see what's going on. So it looks like it's settling down somewhere between 1 and 2. You guys agree with that? And the same thing down here between -1 and -2. Can you tell exactly what that value is? Probably can't from looking at the picture. What could I try?
Use the y bars thing.
Yeah, let's look at a table of values, right? See if we can see if that is heading down to any specific value. So I typed mine into y4. So maybe let's do the left end of the graph first. So maybe I'll start at -10.
Wait,
And
what
then-
did you do Y for?
That's what you put there.
I put my function, tan
Oh.
inverse of x, into y4
Oh, okay.
because I had some other stuff in there. And then I did y1, or the y4 of 100, end of 1,000. Does it seem like we're settling down to something? So it's definitely slowed down the change, right? Does this look like a familiar value?
Isn't it like pi over 2?
Yeah, why would we even be thinking it to be a number in terms of pi?
It's the tangent.
It's an inverse trig function, right? What do inverse trig functions output? Angle measures in terms of radians, because since our calculator is in radian mode. So I'm expecting something in terms of pi. 1.5-ish is about 3.5, or half of 3, right? Half of pi. Pi is 3.14. If I divide, as soon as I start seeing 1.5-ish, I'm starting to think pi over 2. I'm pretty convinced, right? If I check the other end as x approaches positive infinity, I'm not going to do all the inputs. I'm just going to do the last big one that we did. I feel pretty good here, right? So I would say the limit as x approaches negative infinity of tan inverse of x is equal to negative pi over 2. And the limit as x approaches positive infinity of tan inverse of x is equal to positive pi over 2.
You're always listing both positive and negative.
You don't have to,
Okay.
but here's the thing. These are two separate asymptotes, right? So if I wanted all the asymptotes, I do need both of these because I have one horizontal asymptote at negative pi over 2 and a second horizontal asymptote at positive pi over 2. Yes, sir.
Could you potentially put your calculator into degrees, do the same thing, and then just convert it?
Yeah, so let's do that real quick. So degree mode, what am I going to have to monkey with though? Is these x values have got to get much bigger to look at, to get a decent picture of what's going on. I think the y is fine. Nope. What is turned on here? Okay, I put it onto degree. Oh, my apologies. My apologies, the wrong things. Yes, the y's row we needed to change. What should the y's be between? And maybe go by 90s. So there's that. And if you do that, heading towards 90. So sure, could do it the same way with degrees, that's okay.
Then you have to convert the negative degrees into pi over 2.
Yeah, because the standard would be we're doing everything in radians unless like there's a reason to put it in degrees. But your calculator can certainly give you the same things in radians. And there's maybe a little bit more clear that we're heading towards 90 degrees than 1.57 being a number of significance. Sure. So let's say in this question we're asking for all the limits at infinity and infinite limits. What is that going to mean when I look at my graph?
Wait, what did you say before that?
The limits at infinity and infinite limits. Any place there's an arrow, right? Each of these arrows should correspond to one of those kind of limits, right? So how many arrows do I have here? 6 of them. So I should have 6 of these limits that I'm going to write down. Everybody's okay with that? All right. So I'm just going to work from left to right across. Is that cool with you guys? All right. So the limit as x approaches negative infinity of f of x is talking about this arrow. What's that heading towards? Looks like 2. Everybody cool? Okay. We'll go to the next arrow. That's the limit as x approaches negative 1 from the left. That goes to positive infinity. And then the next one is the limit as x approaches negative 1 from the right. That goes to positive infinity. I want to point out for a second, it's worth noting that you could have written this all as one limit and just written it as the limit as x approaches 1 of f of x equals positive infinity. That would be okay. Yes, negative 1. Thank you, John. Next one is the limit as x approaches 2 from the left. And that's going to negative infinity. And then we have the limit as x approaches 2 from the right of f of x, which is positive infinity. And then my last one, the limit as x approaches positive infinity of f of x, which is, looks like 4. So these guys are our limits at infinity. And these ones are our infinite limits. Is that cool with you guys, just from a vocab standpoint? Blake?
So if you have like a function,
Mhm.
there can only ever be 2 like limits as they approach infinity, right?
Yes, I think that's fair. Yeah.
So then it wouldn't be a
I can't think of another situation where, I mean, this might be the only situation that I could come up with. So look at this kooky thing. So like maybe we have a situation like this, where we have something like that. where it's like bouncing back and forth in between.
Yeah.
So I don't know what you'd want to call that thing.
Yeah.
Those limits won't exist when you go to positive infinity or negative infinity.
Okay.
Like that's something that we talk about later on, like it's an oscillating function. But I don't even know I'm trying to think of something where you could get a third one in there somewhere. I don't know that you really can. I think you're probably right, at least for the things you'd see in this class.
Okay, cool.
Without me having to like think of some like really elaborate counterexample, I think you're safe in making that assumption. Paul.
The ones highlighted in yellow are all
Those are the limits at infinity, and the blue ones are the infinite limits. No problem. All right. So, really useful theorem here coming up. And this is when we're doing like algebraic problems, this is something that will make evaluating limits quite helpful. Really, that's...
What is that like? The square root.
No, that's an exponent of r.
Oh, sorry.
So this says the limit as x approaches infinity, positive or negative, of 1 over r is equal to 0. Okay.
Is that just saying that if x's exponent is a fraction, it's equals 0?
And does it have to be just a fraction, though? Rational numbers also include whole numbers as well. So let's take a look at this limit here, and I'll show you how this theorem can come in handy for us. So if I try direct substitution, obviously that's a problem already because I have an infinity in there, right? But even if I did, I'd end up with like infinity over infinity, which is one of these indeterminate forms. That's like super bad news. There's actually like 6 of these indeterminate forms. Oops. So there's 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. These are all called indeterminate forms because there's not like, they don't go to a value, they're not undefined. They're not 0, they're not infinity, they're not 7. They could be like any of these things. So to look at an example here, if I'm doing the limit as x approaches 0 of x over x, if I did direct substitution, I'd have 0 over 0, right? But that limit definitely just goes down to 1 because you can reduce the x's. But if I had the limit as x approaches 0 of x squared over x, well, that's 0 over 0. But that limit should equal 0 because when I reduce the x's and do a direct substitution, I get 0. But what if I had this one where I had the limit as x approaches 49 of x minus 49 over the square root of x minus 7. Again, direct substitution gives me 0 over 0. But if I simplify this, I could write this as a difference of 2 squares and reduce, which would give me square root of 49 plus 7, which is 14. So like all of these things are 0 over 0, but they're equaling 1, 0, 14, right? Like you can get anything you want out of there, really, which is exactly what they're illustrating here. So we really have to be very careful about these indeterminate form situations, that we need a way to kind of work through this algebraically. So here's the trick. So I'm going to take the biggest degree term in the numerator or denominator. In this case, it's x squared. I'm going to multiply the numerator and denominator by x squared, or 1 over x squared, excuse me. So that's going to give me 3 minus x over, 1 over x.
Is that x squared value taken from the numerator or the denominator?
It's the biggest one from
Just
either.
in general.
Yep.
Okay.
So it doesn't matter which one it came from as long as it's the biggest overall degreed term.
It's always going to be 1 over.
Yep. So that gets me this when I simplify, right? When I do that and reduce. Everybody agree? Okay. I'm going to then use my limit laws to rewrite this as the limit as x approaches positive infinity of 3 minus the limit as x approaches positive infinity of 1 over x minus 2 times the limit as x approaches positive infinity of 1 over x squared all over the limit as x approaches positive infinity of 5 plus 4 times the limit as x approaches positive infinity of 1 over x plus the limit as x approaches positive infinity of 1 over x squared. Now I can evaluate this. So it's the limit as x approaches infinity of 3. 3. The limit of a constant is always that constant. Doesn't matter what the x is going to. And by the theorem above, the limit as x approaches infinity of 1 over x is 0. And the limit as x approaches infinity of 1 over x squared is 0. I just have the 2 left over. And the limit as x approaches infinity of 5 is, and then the next limit is 0. I'm going to put the 4 there just to show you that I did something with it. And the last limit is 0. So this just turns into 3/5. What do you notice there?
It was the highest.
It's the leading coefficient. Since the degrees were equal, it was the leading coefficient of the numerator over the leading coefficient of the denominator. Matches up exactly what we saw in Algebra 2.
So, like, can we just do that? Like,
Mhm.
do this? Oh.
No, I'm just showing you how it was working. But, like, goodness gracious, like, that's a pain in the butt. To just be like, I'm just looking at it. What's going to happen if the degree in the numerator is less than the degree of the denominator? You get 0, right?
But what happens if and then if the denominator is less than the numerator, there's no solution.
Well, if the denominator's greater, if the degree of the denominator is greater than the degree of the the degree of the numerator is greater than the degree of the denominator. What happened in Algebra 2? What happened in that situation? That's where you got the slant asymptote, the oblique asymptote. And how did you have to find that? You did polynomial division.
Wait, so this 3/5 steps, this is us finding a horizontal asymptote?
It's the equivalent of us finding a horizontal asymptote. Exactly, because remember we defined a horizontal asymptote as any of these limits at infinity existing.
What happens if the denominator is greater than the numerator?
Then it goes to 0.
Okay.
Because imagine if we had, just for the sake of argument here, Luke, if this was x cubed, let's just do that with blue. So then I would make this x cubed So I'd end up with 3 over x, and that would be squared, that would be cubed, that would be squared, that would be cubed. And I do the limit 0, 0, 0, 5, 0, 0. So you end up 0 over 5, which is 0.
Do we have to prove that, or do we know like immediately when we see that? Can we just say
You can just look at it and do it. And I would say that if it's the reverse for Blake, if the numerator's degree is bigger than the denominator's, and then your limit's going to infinity, then the limit is infinity. If your limit's going to negative infinity, then it goes to negative infinity.
Okay. So it's not that the limit itself doesn't exist, it's just that it doesn't
It's infinite.
it just doesn't actually have an asymptote.
The asymptote isn't a numeric value, right? Remember what one of these, well, we should be really careful here, but like one of these slant asymptotes kind of looked like this. So it would do like one of these kind of things. And if you look at the end, they're still like bombing off towards infinity or negative infinity. They're just not as fast as like a vertical asymptote bombs off, but they're still going there.
Yeah, and they're gonna end up in both positive and like positive infinity for like the top right. Let's just say positive infinity for both the y and the x values.
No, not necessarily. Because that asymptote doesn't necessarily have to be a straight line. Like it could be like you could get like a parabolic shaped asymptote.
Dude.
Yeah. So like, because remember, the part that gave us that slant asymptote was the quotient from the polynomial division. That quotient could be any size polynomial. Now in Algebra 2, you didn't see anything that wasn't a linear polynomial, but there's no reason that doing the polynomial division couldn't give you a quotient that was quadratic or cubic or some other terrible degree polynomial. Sure.
It's crazy.
Yeah. Yeah. But that's like getting beyond the scope of really what is going to happen here. But like, I don't mind the what if questions. These are okay questions. I think that these what if questions really kind of help build your intuition out, right? Like, and that's the stuff that's what you need to be able to do the multiple choice questions quick, is that intuition. It's like I need to understand what I'm looking at and how to look at it a different way. And like, if I change this, what's it going to mean? Because that's what they do in the multiple choice questions, right? They give you something familiar and they'll tweak one little thing and ask you, okay, what's going on now? Right? That's a lot of what you end up getting. So let's say that we have this function. And we're looking for the HAs and the VAs. And we're doing this with our limits. All right. So, you ready to get crazy?
Yes.
What's the issue here? What's the biggest degree on our polynomial?
Actually, wait, JK1.
It's really 1. Why is it 1 and not 2? Because we have the square root on top of it. Yeah. So the way I'm going to write this for the numerator is going to be that way, but I'm going to write it this way for the denominator.
Why is that? Oh, because it's like, okay.
Yeah.
Wait, what?
So So
that you can like actually multiply the x squared in.
right, to multiply that 1 over x squared, maybe I'll do it this way. Is that better? Do it that way. To multiply it into a radical, it also has to be under the radical.
Okay.
So just multiplying by 1 over x doesn't get me inside of the radical. That's why I had to write it that way.
Why are we able to do that since it's not equal to 1? Oh, wait. Yeah, just kidding. It's equal.
Yep, still equal to 1 over x, right?
Yes.
Everybody cool there? So if I then take the limit of f of x, remember I can take the limit of a composition.
What does that mean? What's the
Just throw
Okay.
it in. Just throw it in.
So,
Positive.
so if I look at this, well, actually, let's say this, I can think about that as the composition of two functions, where like
Oh, okay.
g of x is the square root of x, and h of x is 2 plus 1 over x squared, where this is like g of h of x. So if I take the limit of that composition, it's the same thing as taking g of the limit of h of x, right? That's what I'm saying when I say the limit of a composition is the composition of the limits. Does that feel okay?
Yeah.
Do you see what I mean by
I can see that, yeah.
where the, you know, like that numerator is like a root function, but inside of that root function is a polynomial, right? That's two separate functions composed together.
That makes sense.
Okay. And again, if I'm using the vocabulary and you're like, yep, you lost me with that vocab, that's okay. Stop me and ask. We can re-explain. Everybody okay with this?
I guess I'm just so confused on how you got the square root of 2 plus x not there.
When I distribute this,
Yeah. Oh, wait.
that gives me 2, and I distribute that, I have 1 over x squared. Because Anise, like, if I have the square root of 2 times the square root of 3, that's the square root of 2 times 3, right? Where I can just put them together under the same radical. So I have like the square root of 2x squared times 1 over x squared plus 1 times 1 over x squared. So that's just 2.
Yeah.
And that's, oh boy. And that's just 1 over x squared.
That makes
more sense.
Luke?
So, you lost me right at the beginning when you did the multiplied by square root of 1 over x over 2 over 1 over x.
Okay.
How did you choose those numbers?
Well, they're the same. If I reduce that, they're both 1 over x, right?
Yes.
So the reason I used the square root of 1 over x squared is because to multiply that into the radical, I had to have a square root around it.
Okay.
So I just rewrote 1 over x as the square root of 1 over x squared.
And then the reason you only chose 1 over x was because
There's no radical in the denominator, so it doesn't need a radical around it to be able to multiply those things.
Okay. So you wouldn't do x squared because of the square root that surrounded it?
Correct, because this 1 over x squared square rooted is just 1 over x. right? If I simplify the numerator there, 1 over, or the square root of 1 over x squared, that's just 1 over x, right? So I have 1 over x over 1 over x, just multiplying by 1 then. Is that okay?
Yeah.
Paul?
So in the denominator, on like the top line, you go from 3 minus 5 over x, and then then you go down.
Oh, sorry, I forgot the 5 here. Is that,
Yeah.
there you go. Still 5 times 0, so it goes away.
Oh, because 1 over x. Yeah, okay, that equals, okay.
Yep, thank you. Tegan?
I'm confused why you made the g of x and the h of x.
So that was just Blake saying, when I said the limit of a composition is the composition of the limits, Blake was like, what composition are you talking about? And I was explaining to him how that numerator was the composition of a square root function and a polynomial.
Okay. And then you had to take the 5 out because in order for like the theorem to work, it had to be a 1 in the numerator.
I mean, that's what the theorem says, but it's fine if it's just a constant. It's still fine. It still works. John.
Does that have to check the negative infinity, or is it just the negative?
So we found, so as long as you have one or the other, that's an asymptote. There is still a problem with what we've done here, though.
Oh, wait, going back to what you said. So actually, I'll just let you.
Okay.
I'll see if I can push it.
So the problem is here. Why is that a problem? We said that simplifies down to 1 over x, right?
It's plus or plus.
It's really the absolute value of 1 over x. So there's a possibility that that also could be a negative here. So we should also have this one.
Is it because of the square root function?
Well, the square root of 1 over x squared is the absolute value of x, or is 1 over the absolute value of x. Because anything I take the square root of had to have been a positive value, right? So if I simplify that down, I'm only going to get 1 over positive values of x. So I could have negative still. So I have to also do this again with like a negative sign stuck there. And that's why I'm getting this piece, which is super not obvious, right? Yeah, that's a tricky one. Now, if you looked at the graph, would you have caught that? Yes. What would be the problem? Is if this was a no calculator problem, right? Then you're in a lot of trouble. Unless you notice that, which is tough to notice, be honest with you. We'll pause here. We'll finish this problem next time.